So far this semester, we've basically been dealing with a single force. So we've been working problems that in one capacity or another have dealt with electric forces. Now we're going to add a new force, and we're going to talk about magnetic forces. So to set this up, let's look at basically the three forces that we're now going to have that relate to a field. So the first one, of course, is the gravitational force. And we said you get the magnitude of the gravitational force by taking the mass and multiplying it by the magnitude of the gravitational field. The electric force, we said you can calculate the magnitude of that by taking the absolute value of the charge and multiplying it by the magnitude of the electric field. And so what we're adding now is the magnetic force. And again, you can see that it's got a similar structure with a couple caveats. So let's go through here. This again, Q is still charged, so this is the absolute value of the charge. V is speed, so this is from a velocity vector. B here is the magnetic field, and then this sine phi term, phi is the angle between the velocity vector and B. So what's this velocity vector? Well, for starters, it's the velocity vector for your charge Q. So in the same way that we said, hey, Q sitting in front of E is what matters. Well, QV, so both the charge and how it's moving, right? Because again, this sine phi is a description of how it's moving. That has to pair with the magnetic field. So the QV is basically playing the same role as mass did for gravitational forces and charge did for electric forces. In terms of units, well, if we take this equation and rearrange it, right, so our sine term is unitless. I divide forces by charge and speed. And basically what that's going to give me, it's going to give me newtons divided by coulombs times meters per second. And all I'm doing is rearranging it so that the coulombs per second, that's an amp, times meter. So this is just sort of rearranging the unit to solve for it. So this is one way in which I can write it. So the units of magnetic field are newtons per amp meter. And that has its own name. That's called a Tesla. So the Teslas are going to be our SI units for magnetic field. All right, so let's sort of big picture here, make sure we understand conceptually sort of what each of these three equations are telling us. So for starters, our first equation is telling us that masses feel gravitational forces and masses cause gravitational fields. So all of our forces are interactions between two objects. And so for a gravitational force, it's the interaction between two masses. One mass you put, so one mass causes the gravitational field, the second mass you put into that gravitational field and it feels a gravitational force. The electric force, well, a charge is going to feel an electric force because charges also cause electric fields. So again, the interaction here is between two charges. So you've got one charge that's causing the electric field, then the second charge is feeling an electric force by being in that electric field. So what's our magnetic force equation telling us? Well, basically, it's telling us that moving charges feel magnetic forces. And what we'll see is that, sure enough, moving charges cause magnetic fields. So really, in the same way that the gravitational force is an interaction between two masses, and the electric force is an interaction between two charges, the magnetic force is the interaction between two currents, because that's what moving charges are. So we're gonna be able to figure out what the magnetic field is that's caused by some current, and then how some moving charge reacts or feels that magnetic field through the magnetic force. So that's the idea. Masses cause the gravitational force, charges cause the electric force, currents cause the magnetic force. So let's come back to thinking about the relative direction of the velocity vector in B. So again, here I've got a moving charge. Here's a situation where I've got a moving charge moving to the right I've got a moving charge moving to the left. Both of these are moving in a magnetic field that, again, our field lines are showing us points to the right. Well, in this case, that means that the velocity vectors of these two charges lie along the same lines as the magnetic field. So for this charge, velocity, magnetic field point in the same direction, so our angle phi is 0. For our second charge here, the velocity vector points in opposite the direction of the magnetic field, so phi is 180, but whether it's 0 or 180 doesn't matter. The sign of that angle is still 0. So neither of these two charges, even though they are moving charges, neither of them feel a magnetic force because they're moving along the line of the magnetic field. So instead, what I'm interested in is when I have moving charges that don't move along the line of the magnetic field. So here's a situation where it's moving in the plane of the magnetic field, but it's now at some angle. And so what we care about here is how much of that velocity, how much of the velocity can be broken into a component that is perpendicular to the magnetic field. Because the sign term tells me the larger I make that perpendicular component, right, the bigger or the closer to 90 degrees angle phi is, the larger the magnetic force is going to be. The other thing you'll notice is the magnetic force happens to be perpendicular to the plane of these two vectors. And we'll talk in class about a right-hand rule that we'll use to figure out what the direction of the magnetic force is going to be. Now, if I have a particle that's moving at right angles to the magnetic field, then that's going to have the maximum magnetic force. Right? So the closer this velocity is to lining up with the magnetic field, the smaller the magnetic force will be. The closer it gets to being perpendicular to the magnetic field, the larger it'll be. So because, again, that's coming from this sine term, and the sine of 90 degrees is as large as you can make that sine of any angle, that's just 1, that's going to be when the magnetic force is at its maximum. Well, we said that really what's going on in a magnetic force interaction is the interaction between two currents. And so instead of talking about the magnetic force felt by a single moving charge, we can talk about the magnetic force felt by a current-carrying conductor. So if I take some conductor that's carrying current, so a wire, and put it into a magnetic field, I can calculate the force felt on the wire by that magnetic field, and it's given by this expression. So the magnitude of that force is given by, again, what's the amount of the current, what's the length of the conductor in the magnetic field, and then what's the magnetic field strength, and then our sine phi term, well, phi is now the angle between the direction of the current flow and the magnetic field. So you'll notice that, again, this tells us that if the current is flowing along the same line as the magnetic field, that conductor won't feel a magnetic force. So that wire won't feel a magnetic force. If, on the other hand, that wire happens to be perpendicular to the magnetic field, so that the current flow is perpendicular to the magnetic field, then I'll have the maximum force that I can, and that's just going to be magnitude of current times length of the wire times magnitude of the magnetic field. So we'll play with these two scenarios for calculating the magnetic force, and then again we'll talk about the right-hand rule for figuring out its direction. So we'll have both a magnitude expression, a way to calculate the magnitude, and a way to calculate a way to determine the direction of the magnetic force.